Hi guys, welcome to this set of videos, and what we're going to be doing here in Chapter 7, Section 8, which is maybe my favorite section in all of Algebra 2. And here's the reason why I like this section so much. Frequently as a math teacher, I hear kids say, why? Why do I need to know this? What's the point of all of this Algebra 2? When am I ever going to use it? Well, here you go. This is the section for you. Chapter 7, Section 8 is going to be nothing but word problems, real life situations and scenarios showing you exactly how exponential and logarithmic functions can be used to mathematically model and predict natural phenomenon, right? Really excited about this section. I love going through this section, so I can't wait to get started on it with you. But before we jump into it, I want to give you some objectives or learning targets that'll kind of help you focus as we make our way through this set of notes. Up first, what we're going to do is we're going to use logarithms and exponentials, use logarithms to solve problems involving exponential decay, and we will use logarithms to solve problems involving exponential growth. All right, so exponential growth and decay, we're going to do all sorts of problems here, everything from chemistry to biology to population growth. We got all kinds of stuff in here. Like I said, Chapter 7, Section 8 is nothing but just solving sort of real world problems using the math we've learned here in Chapter 7. So let's go ahead and jump right into this. First, let me give you the formulas you're going to need to be successful here in this section. And they're actually all formulas that we have already seen. Up first, let's talk about growth. So this is going to be exponential growth. And as promised, I told you guys in Chapter 7, Section 1, we saw this exponential growth equation. And I told you that it would come back in Section 8. Well, here it is. So what we've got is our exponential growth equation. This is exponential growth. This is if you're given a rate as a percentage. All right, so you will use this exponential growth equation if the rate equals a percentage. All right, if you're given the rate as a percentage. Now remember, you can't actually use the percentage in the problem. You have to convert that to a decimal, but you're just looking for a percent. When we start the problems, if you're reading through and you see that it increases by 12%, you know you need this exponential growth equation. However, we also got in the previous section a continuous exponential growth equation where we use the natural base e because it is continuously growing. In which case, you'll use this problem. Oh, sorry, I don't want that. I want my highlighter. You'll use this formula in the event that you are given a growth constant. Keep in mind here that k is a constant. It is the constant of, oh, I apologize, that is a typo. That should be growth. Is the constant of growth, and here's what this means. K is the growth rate. All right? So we're replacing R, which is a percentage in this equation, and instead we'll be given problems where the growth rate is given to us as a constant. It'll be some number. Generally, it'll be pretty small numbers. They'll be decimals, but it doesn't have to be. I mean, K could, depending on the problem or the situation, be anything. But K is going to be the growth rate. It'll represent the rate, and it'll be some constant. So if there's anything in the problem about a growth constant, or it asks you, in several cases will ask you to actually find K, well, right, this doesn't even have a K in it. You've got to use the continuous growth, continuous exponential growth formula, that one right there, which has our natural base E in it. Okay, the other way that these problems could go is then, of course, going to be decay. Well, if you have decay, again, two formulas. This one we got back in Section 1 of Chapter 7, and I told you when we looked at it, it would come back in Section 8. So there it is. Again, if you're given the rate as a percent. Obviously, you can't use the percentage in the formula. You'll have to convert it to a decimal. But if you've got a problem and it gives you a percentage, you're going to need to use, you've got a sale going on, right? And the item is decreasing in price by 5% each week, right? That it's going down, the price is decreasing, and they gave you a percentage. It's decreasing by 5%, right? You're going to use the exponential decay formula. But what if you have continuous decay? Well, continuous decay is going to require the natural base exponential e. And in this case, it's going to be decay, right? Because we have our k, which is the constant of decay. K is the constant of decay. But we know it's decay because now k is negative. So negative k is the decay constant. Or, I'm sorry, the decay rate. So, very, very easy to know which one you're going to need. The problem will very clearly, just by reading the problem, you'll know whether you have growth or decay. That'll sort of jump right out at you, in which case then you've only got two options, right? You got two formulas for growth, two formulas for decay. How do I know which one to use? Are you given a percentage? Or are you not given a percentage? All right, easy peasy. Let's go ahead and jump right into this and start doing some problems on the next page of the notes. So head on over. I'll meet you guys there.